Okay. Did anybody have a question? No. Does anybody have the textbook with them? I just realized I didn't bring it with me.
And I'll get the graded lab, or the lab solutions.
Thank you. Make sure you get it at the end of the lecture. I don't want to walk away with it. Okay. Let me start with a couple of announcements. Homework is due today. It was a combination of problems from Oppenheim and Schaefer, and also some lab stuff. Pick up the solutions to this homework that's due today on your way out. Midterm is Wednesday, October 22nd. It's in Sibley Auditorium, 9:30 to 11. You can bring one sheet of 8.5 by 11 worth of formulas, and pick up the graded labs on your way out. Dan, do you have any other announcements to make?
Maybe the paper for the midterm?
Yeah, bring along, my recommendation is to bring along a blue book so you don't have to staple it, or if you don't bring blue book, you bring a bunch of white sheets to write down. Bring a little stapler with you so that no pieces of your paper get lost. There won't be any argument that my thing got lost and stuff like that. Okay? And the midterm covers through FR filter design using Windows. Yeah.
Will there be a review session?
Will there be a review session?
I'll do office hours on Monday, but so you can come in and ask questions. But as far as the review session, I'll probably do what was in discussion this week. Fully decided.
So there will not be a review session?
No, not a specific review session, but if you guys have
Do you want to have one on Tuesday, maybe, just for completeness? Can you make it?
On Tuesday at night. I'm not sure what room, how the rooms would work. But,
You can post it on the web about the room later, but if you think...
Would I just have to reserve a room?
Yeah, you can go to Rosita and she will reserve a room for you.
Then I guess we'll do one on Tuesday at what time am I out? Sorry, it's 4 o'clock. Why don't we, since we canceled discussion sections for next week, we canceled discussion sections.
Why are we canceling discussion sections?
Because one lies before the exam and one lies after the exam, so it's kind of hard to.
Why are we canceling the discussion section before the exam? I think it's good to.
Well, what I can do is put the review. in that slot.
Okay, let's just say there'll be a review session.
Why don't we say review session from 2 onward? So
Well, why don't we just say review session from 4 to 5, which is when the discussion was?
discussion was 2 to 3.
Oh, 2 to
And
3?
then office hours are 4 to 5, so I figure we can just kind of fill that
Okay.
block of time with
Okay, so review session will be, what did you say, 2 to 5?
2 to whenever
Right.
people like
Right.
that stuff.
So if you don't see any announcements, it start off being at 2 to 3 in the regular discussion session. Where is 2 to 3? Which room is that?
It's the, what's the room there? 291 or something? 293? 290, I don't know. It's the one right by the elevators. Hopefully, guess. It's on the website. I think it's 291.
Yeah, wherever the regular discussion section on Tuesdays is, this is where the review session will be. And then there's office hours on Tuesday, so this is Tuesday. There's also office hours on Tuesdays from 4 to 5, so you can hang around and ask more questions, but probably the review session will probably last from 2 to 4. And what Dan's going to do is check with Rosita and announce the portion from 3 to 4 is where we might not have a room.
There's no one in there, so
Well, it changes. If in case it changes, try to get that same room. In case it changes, you put it up on the web, and you also leave a note, a paper note outside the room where the normal discussion section is, saying where the continuation of the review session is from 3 to 4 on Tuesday. Okay. Any other questions or comments? All right. Let's do a quick show of hand for this last homework. How many people took less than 5 hours to do it? How many between 5 and 10? Okay. 10 and 15? And 15 and higher. Okay. All right, very good. Let's get going on today's lecture. I'm anxious to talk about this optimal filter design stuff. So what we talked about last time was sort of problem formulation and some observations. So in particular, could you zoom the camera or shift the camera this way? Thank you. Right. In particular, what we talked about was this polynomial, a of n cosine omega and g of omega. We called that a trigonometric polynomial. And we talked about how many local extrema it could have, and we found out that it was n plus 1. And then we embarked upon the problem of optimal FIR filter design. And what we said was that you start with the basic problem statement, which is you're given a set of specs like this. We're designing a low-pass filter in this example. You can easily be generous to anything you want. You have ripple specs here, ripple specs in the pass band, in the stop band. This is your transition band. And you want to find minimum FIR filter with minimum number of coefficients that satisfies the specs. And then we went and talked about if you reduce that problem to problem B, which says given omega p and omega s, the pass band, the stop band frequency, and m, which is the number of taps, and k, the ratio between the ripple and pass band and stop band, determine A such that delta 2 is minimized. So this is problem B. And what I convinced you of is that if you solve problem B, if you have an algorithm or a box, a black box, let's say, that given these inputs minimizes delta 2, finds A of n such that it minimizes delta 2, then we talked about the fact that if you had a box doing that, then you can use that in an iterative scheme like this in order to solve the bigger problem, problem A. Okay? And we stop right there. So now my job is to show you how to solve problem B, which is really this problem that's stated here. And the way I'm going to do that is reduce it to yet another problem, problem C, which I'm going to talk about right now. Okay, so so the topic of discussion is optimum FIR filter design, and sort of the review from last time. We started with problem A, and we reduced it to problem B. And today what we're going to do is talk about problem C. And then finally we're going to show you how to solve problem C. And then once you solve problem C, you go backwards and you've got the main problem done. So just as a reminder, in today's lecture, problem B, just the statement of it, I'm not going to show that solving problem B is equivalent to solving problem A, but the statement of problem B is as follows. Again, just to set everything up, this is the problem statement, delta 1 here, delta 2 here, omega p here, and omega s here. Could you shift down so that the entire paper is shown? Thank you very much. So problem B was given omega s, omega p m, which is the number of taps, and k, which is delta 1 over delta 2. Given all of that, find A of n to minimize delta 2. This was problem B. So you have a box here, there's various inputs coming in, and this is algorithm B, and out comes A of n and the resulting delta 2 that got minimized, and the input is omega s, omega p, m, and this k guy, which is the ratio between delta 1 and delta 2. Okay, so that's just the setup. And what I'm going to embark upon now is to tell you what problem C is. And first I'm going to write down the statement of problem C and then show you that it's equivalent to solving problem B. So problem C is as follows. First I define this function E of omega, which is W of omega times G of omega minus D of omega, where now I have to define what all these functions are. Well, W omega is a positive weighting function. And it's equal to 1 over k over some interval I1, and it's equal to 1 over some other interval I2. And G of omega is the good old thing from last time's lecture, which is just the summation from n equals 0 to m of A of n cosine omega n. And D of omega is just the desired frequency response. And it's given by 1 in interval 1, and it's given by 0 in interval 2. And you can already, from this write-up, you can already see what I1 and you can already guess what I1 and I2 are. Well, I1 seems to be the pass band, and I2 seems to be the stop band, right? And so given all of that, problem C says, find A of n to minimize the following quantity that I'm going to write in this box. Maximum of absolute value of E of omega for omega in some set F, where F is just the union of I1 and I2. And in particular, F is a subset of a closed interval omega in between pi and 0. Okay. So if I were to plot what F looks like, this is 0, this is pi. I1 is this interval, goes from 0 to omega p, and I2 is the stop band, goes from omega s to pi. Okay, so F in general is a union or is a subset of this closed interval. In this case, it's the union of I1 and I2, which is our passband and stopband. So let's say, let's write down I1 is passband, and I2 is the stopband. And does everybody know what I mean by a closed interval? It's a term from real analysis. You have intervals that are closed and there are intervals that are open. Anybody took real analysis? Yeah.
Closed interval to interval means every convergent sequence converges to a point inside the interval, a point that belongs to the interval.
Not quite. There was one other person. Really? It means that there's something wrong with what I... Closed interval typically means that the endpoints are in it, as opposed to open intervals where... Pardon? Oh, did I? Interval. Did you hear interval? Yeah. That definition could be equivalent to what I'm saying. I bet it is. But an easier way of remembering it is a closed interval where is the ones where the endpoint, let's say I have an interval omega s to pi. So people sit down and argue, is omega s itself in the interval? It's sort of like students arguing when you say it's Tuesday. Is it Tuesday morning due, or is it due Tuesday evening, etc.? But anyway, the same thing with intervals. Mathematicians argue, is the end point of the interval, which specifies that omega s, is it in it? Is the omega itself in the interval or not? And the closed interval, omega s, for example, if I talk about closed interval omega s to pi, that means pi is in it and omega s is in it. In contrast, if I have an open interval from omega s to pi, I can get arbitrarily close to omega s. Really, really, really close. All of those are in the interval, but omega s itself is not in the open interval. So that's the, I think your definition is also equivalent to what I just said. Okay? So here's problem C, and some of you might be a little bit petrified in that it doesn't even look anything like problem B. But could you zoom out so the entire page can fit in? Just great, thank you. So some of you might be a little bit worried that this is remember problem B was this. You're giving omega s, omega p, m, and this k, the ratio guy, and you want to find a such that you minimize delta 2. Here, you're minimizing something else, and there's intervals coming up, and there's other things going on. So I spend the next 2 minutes to convince you that problem C is essentially equivalent to problem B. Okay? So what I want to show is that problem C is equivalent to problem B. In particular, I want to start by showing that theta, which I call this quantity, this blah here, this whole thing, I'm going to start calling it theta. Maximum of absolute value of E of omega for omega in the range in the set F, right? That's too much. I just call it theta. But anyway, I want to start showing that theta is equal to delta 2. At least the thing we're minimizing should be the same, right? In both cases, problem B and problem C, we're finding A of n to minimize something. That something is here in problem C, and it was delta 2 in problem B. So let's start by showing that. And then the rest of the stuff is a little bit easier. So how do we go about doing that? Well, I'm going to have to start playing with this animal, this theta guy, which is maximum of omega in F of absolute value of E of omega. I have to show, and I put question mark here, that that is equal to delta 2. So let's start by writing down the definition of E of omega. Well, E of omega up here has all kinds of things. It's got W of omega, G's, and D's. So let's plot all of these as a function of omega. So W of omega, we have a definition for it up here. It's given by here we go. It's given by 1 over k in the passband in I1 and 1 in I2. So if I were to plot the W of omega, this is 0, omega p, omega s, pi. So based on this definition, it's 1 over k here, and it's 1 here. That's what W of omega looks like. Okay. And to figure out what E of omega looks like, I also need to know what D of omega looks like. What D of omega we're given by that. D of omega as a function of omega looks like it's 1 all the way to omega p. And it's 0 for the rest of it. And so then E of omega is just W of omega, G of omega minus D of omega. And so what that means is that E of omega over W of omega is nothing but G of omega minus D of omega. And what that means is that G of omega is nothing but D of omega plus E of omega over W of omega. So if by definition we call maximum value of E of omega theta, we call maximum value of E of omega absolute value for omega in the range f, we call that to be theta. What does that mean about shape of E of omega? How could I plot shape of E of omega? Well, I can plot it as follows. What that means is that if I were going to, as a function of omega, 0, omega s, omega p, and then omega s to pi, if I were to plot E of omega, so if absolute value, and we only care about in the range f, and f is the union of this region and that region. It's the union of I1 and I2. And this is E of omega. So if absolute value of E of omega is maximum value of absolute value of E of omega is no bigger than theta, what range of values can E of omega have? Between plus theta and minus theta, right? So here's minus theta, here's plus theta, and this is the maximum value of it over for omega in range f, and f we just defined as union of I1 and I2. F is this plus that, okay? So it's a subset of this interval pi. So E of omega itself in this range can be anywhere here, and that's why I shade it. And in this case, it could be anywhere here. Again, I shade it like that, okay? And similarly, as a function of omega, I can plot now E of omega over W of omega. And what is W of omega? Well, W of omega I already plot here. It takes on the value 1 over k for this range, for I1, and it takes on the value 1 here. So given that E of omega looks like this and W of omega looks like this, E of omega over W of omega, how does it look like? Well, between 0 and omega p, and then between omega s and omega pi. So between omega s and omega pi, it's going to look like the same. I divide this by 1. So it's the same thing. So if here it was between plus theta and minus theta, if I divide it by 1, it's still between plus theta and minus theta. So minus theta plus theta, it still remains in that range. And what happens in this other range? Well, it's between plus or minus theta here, but then divided by 1 over k. So it can go all the way, theta divided by 1 over k is theta times k. So you can go all the way theta times k here and all the way minus theta times k here. So let's just plot that. So you can go all the way to minus theta k to plus theta k. Okay? Yeah, question.
In the omega plot, it seems like k is less than 1.
K can be either less than 1 or larger than 1. The way I've been plotting it, I'm assuming it's larger than 1. I'm sorry, smaller than 1. Oh, I see what you're saying. You're saying here, I've made k to be smaller than 1. And here, I just flipped it. Good point. Sorry about that. It doesn't make any difference, but let's do the drawing. The point is, k can be either smaller than 1 or bigger than 1. But since I've plotted here for larger than 1, let's smaller than 1, let's do it. So let's, good point. E of omega over W of omega. And so this is plus theta, this is minus theta, this is plus theta k, and this is minus theta k. So between 0 and omega p, it's in this range. And between and between here is this other range. Between omega s and pi, it's between plus theta and minus theta. Okay? So given that, now how can I plot, coming back to these relationships that we draw? So this is E of omega over W of omega. Now I'm going to have to draw D of omega. Well, if I draw D of omega, so D of omega looks like this, right? It's 1 here and 0 here. If I add now D of omega, which is this plot, to E of omega plus W of omega, so recall, let's say, G of omega is just D of omega plus E of omega over W of omega. So let's just add D to this thing and get a plot of G. So what do we get? Well, D looks like this. So D looks, can you zoom out? So D looks like this, and E of omega over W of omega looks like this. When I add them all together, I get G of omega looks, I have to add 1 to this thing, so it'd be 1 plus theta k, 1 minus theta k for this range, 0 to omega p. And for omega s to pi, it's 0 on top of plus or minus theta. So okay, that's omega s. So this would be 1. This would be plus theta all the way to minus theta, right? So that's how G of omega looks like. And how did our G of omega from problem B or from problem A look like? So now, so this is our G of omega as done in problem C, right? Now, the question I'm asking is, how does G of omega look like as in problem A or problem B? It doesn't matter. The G of omega didn't change. Well, our plotting was what? If you go back to last time's lecture, the first thing that we plotted was this thing. Magnitude of g of omega had a ripple amount of delta 1 here and delta 2 here, right? It had delta 1 ripple here and delta 2 ripple here. Or if you can even go back to the first page of today's lecture, here. This is magnitude of h of omega, which is the same as g of omega. It has ripple of delta 1 here and ripple of delta 2 here. So if I were to drop this is magnitude of g of omega. So if I were to drop magnitude of g of omega, what thing would I get? This is centered around 1 here, and this is magnitude of g of omega. That's why delta 2 that's why we're only positive here. So if I were to draw g of omega itself, it would look something like this. It would have, here's omega p, here's omega s, all the way to pi. It would have plus delta 2 going all the way to minus delta 2 here. And then it would have up here, it would have, this is 1 minus delta 1, and 1 minus delta 1 here, and 1 plus delta 1 there. Right? So what I want you to convince yourself is this. If I have magnitude of g of omega that has ripple of delta 1 here and delta 2 here, the g of omega itself could be 1 minus delta 1, 1 plus delta 1 range here, and delta plus delta 2 or minus delta 2 here. Okay? Is this clear? All right, now this is my g of omega as defined in problem C, and this is my g of omega as defined in problem A and B. So comparing these two things, what can I conclude? And we sort of already know here, this k, this number k that I've been throwing around, is the same k as in problem B. It's delta 1 over delta 2. K is the same as delta 1 over delta 2. So, and this k is the same as that k. So if g of omega was 1 plus theta times k, in other words, 1 plus theta times delta 1 over delta 2, what should k be so that this g corresponds to the same as g? What should theta be so that this g of omega corresponds to g? What should, again, theta be such that this ripple corresponds to that ripple? So what should theta be? That's right. So conclusion from all of this is to make these two problems equivalent, theta is the same as delta 2. So if I make theta to be the same as delta 2, I get 1 plus delta 2 times delta 1 over delta 2, which is 1 plus delta 1, which is the same thing as I have here. This theta is the same as delta 2. Everything matches up. Okay, so essentially in problem in problem B, we were given all these omega s, omega p, m, bram, 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 and we wanted to find a of n to minimize delta 2. Now we reformulated that problem C. We want to maximize these. We want to minimize this, and so we want. So the only two way these two problems can be the same is that this theta, which is this thing, is the same as delta 2. So conclusion that I want to get from all of these things is that problem C was find a of n to minimize theta, and problem B, find a of n to minimize delta 2. And these two are the same problem. So where we are now is, again, we started with problem A, we reduced it to problem B, and now we reduced it to problem C. And now I'm going to come up with a way of solving. Now it's time to bite the bullet and actually solve problem C. And how do we go about solving problem C? Well, you solve problem C by using what I mentioned last time, alternation theorem. Okay? So alternation theorem. And how does that go? Well, that has its own set of statements and ifs and thens and things like that. So, but let's just state it as it is and see where we go from it. So what alternation theorem says is the following. It says, suppose there's a lot of assumes. So let's just write down all the assumes. You say F is again union of closed intervals. We already sweat over that, what's closed intervals, a second ago. And let P of x be an nth order polynomial. Nth order polynomial. And I already told you that polynomial theory from approximation theory has been very, very helpful in filter design problems. But let's write down what we mean by P of x is the summation from k equals 0 to r, a sub k, x to the k. That's an nth order polynomial. And d is some desired function. Desired function that's continuous in f. And let w be a positive function. And I'm deliberately using the same notations as I used in problem C, so you can see the link as to how alternation theorem can be used to solve problem C. So w is the same as w we had before, d is the same as d we had before, and let's define E of x to be w of x times d of x minus P of x. That's becoming very similar to problem C. What we had before was E was wg minus d. Here we have is wp minus d. Okay. Define norm of E to be maximum of x in f of absolute value of E of x. Well, that's the same thing as we had before. That's our theta, which we just showed delta 2 is the same as delta 2. It looks really promising. So given all of that, so this is our if part, or assume, then, this is the then part. The necessary and sufficient condition for P of x to be a unique nth order polynomial that minimizes this is that E exhibits at least r plus 2 alternations. And I have to define what all of these things mean. Or I have to define what alternation means, etc., etc. So that's the if part. And then it says the necessary and sufficient condition for P of x to be a unique nth order polynomial that minimizes norm of E is that, and remember, minimizing norm of E is our goal, right? This is the thing we wanted to minimize to problem C. We showed this is the same as delta 2. This is the thing we wanted to minimize in problem B. So that's our goal. So this is straight on, like a bullseye to what the problem we're solving. It says the necessary and sufficient condition for this polynomial to be a unique, and I underscore unique, nth order polynomial that minimizes this is that what? Here's the thing. E of x exhibits at least, and I'm going to underscore at least, r plus 2 alternations. And I'm going to define what alternation is, i.e., there is at least r plus 2 values of x such that values of x, which I'm going to define it by x1 smaller than x2, all the way x r plus 2, such that these are the r plus 2 values of x. That is what I mean by alternation. E evaluated at x sub I is always negative of E evaluated at x of I plus 1. And is equal to plus or minus norm of E. This is a really loaded theorem. There's a lot to explain. And after you copy it, I'm going to start highlighting the important parts and explaining it. So I want to have your full undivided attention. Okay? So if you just zoom out just a little bit so that we can have as much of this in one page, great. Stop. Okay, so this is the statement of the whole thing. You have F union of closed intervals. That's the same as what we had in problem C. P is an orthoorder polynomial. D is the desired function. W is positive. This part is almost carbon copy of problem C. So the ifs are all identical to problem C. Good. So this is solving our problem. Now, but what does this thing say? It says the necessary, and it's telling us what the necessary and sufficient conditions are so that polynomial of P minimizes E. And were we hoping that to minimize E? Absolutely. That was our goal. This is the thing we wanted to minimize. Maximum of E of omega in F, which is maximum of E of omega in F. I've just replaced omega with X. It doesn't matter. So we do want to minimize this. So, and this is telling you the necessary and sufficient condition to do that is for E, this function, to exhibit at least R plus 2 alternations. And what do we mean by alternation? That means there has to be R plus 2 values of X. I call them X1, X2, X3, X4, all the way to X of R plus 2, such that the value of E at X1 is negative the value of E at X2, for example. And then the value of E at X2 is negative a value of E at X3. The value of E at X4 is negative value of E at X3. Right? That's what this thing is saying. And these guys are all equal to plus or minus norm of E. That when what's the norm of E? It's the value that this thing attains as its maximum. So this thing is a pretty loaded statement. So pictorially, what's happening here is, how does E look like then? What's this E of X guy looking like, plotted as a function of X? It says that E over the interval F has a maximum, which is norm E. And what it says is that this thing is going to attain its maximum in an alternating way. And there's at least R plus 2 of them. That means it attains plus norm E here, and then it attains minus norm E here, then it attains plus norm E here, minus norm E here, plus norm E here, minus norm E here, plus norm E here, and I'm running out of space, minus norm E. So it says if P of X is of the order R, there is at least R plus 2 of these guys. And so this one is X1, this one corresponds to X2, this one corresponds to X3, this one corresponds to X4, this one corresponds to X5, X6, X7, X8, etc. So if it were after a fifth order polynomial, alternation theorem tells us there's at least 7 of these. 1, 2, 3, 4, 5, 6, 7. If we're after a seventh order polynomial, alternation tells us there's at least 9 of these. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? But it could be more. So it can't, for example, this thing cannot achieve, again, what the consequence of this alternation theorem is that E of X, for example, we cannot, if it looks something like this, so we call this X1, and it achieves plus norm E, and let's say X2 achieves minus norm E, and X3, it didn't achieve plus norm E. X4, it achieves minus norm E. Alternation theorem, it tells you this cannot happen. Let's put a big cross. Why? Let's put a big red cross on it. This, by alternation theorem, this cannot happen. Why is that? Because because if I order these x's as small to big, x3, because it doesn't attain plus e at its maximum, it cannot be an alternation. And you say, okay, the hell with it. We just throw away x3, and our alternation points are x1, x2, and x4. It can, because it doesn't alternate, because this is plus, minus, and then you hit another minus again. So it has to alternate, and it has to alternate to plus norm e and minus norm e. There is no wiggle room. Yeah. Yeah. You could also throw away x4, but then, yeah, you could do that, but as long as you have enough alternation, that's called that x3. As long as, if a polynomial was of order r, as long as you get your r plus 2 alternation, at least, you have to have that many. Then you're okay. Is that what you're going to ask, Kevin, also? Yeah. So that means this can't be an alternation either. Correct. So, so as it turns out, when you solve problems in this, you see that this is a pretty strong condition. It characterizes how your solution is going to look like. And it's good that it characterizes how your solution looks like, because the fact that it nails the characteristic of your solution, it enables you to find it, as you'll see in a minute. But I want to emphasize one more thing here. And what's that? This thing that I underlined. It's a unique. That means that there's only one polynomial that does it. Not 2, not 3, not 4, just one. So if your goal, if you're dealing with polynomial of degree r, like degree 5 or something, and by the way, this degree r, what does it correspond to in our original filter design problem? It's the same as the number of taps in our filter. Before, our polynomial was g of omega summation from n equals 0 to m, and we had m plus 1 taps, right? Now it's disguised as p of x, with p of x being summation from k equals 0 to r. So r is the same as the number of taps that we have. So if you're designing a 4th order polynomial, a 4th order filter or 10th order filter, whatever, and you're trying to do this minimization, there's only one thing that does it. Not 2, not 3. It's unique. And also the last thing I want to emphasize in this statement here is the necessary and sufficient condition. And that has a special meaning in mathematics. What does it mean? It means that this is necessary to happen. That means if it doesn't happen, p of x won't be unique polynomial minimizing that. It has to happen. There's no wiggle room around it. That's what that means. All right? And when it says it's sufficient, that means that's all we need to happen. No more conditions. It just means what it says. Necessary means that this has to happen. No way for it not to happen. If it doesn't happen, the thing won't be true. Sufficient means, and that's all that's needed for it. That's all the conditions we need for this uniqueness thing and for the minimization thing to be true. No more. I can't pull another condition off the top of my head and say, oh, this has to hold true, this has to hold true. This is it. This is all we need for the whole thing to hold true. Okay? So, but, even though yeah. Even though this problem, are there any questions? Let me pause for a second. Yeah. Even though this looks awfully similar to problem C, I'm going to have to now spend a little bit of time relating it to problem C, in particular relating it to problem A. Okay. So let's do that right now, the next 20 minutes or so. So having stated alternation theorem, now I want to go back to that observation we made in the last lecture, right? And that about the number of local extrema of g of omega. So recall that g of omega that as of last lecture, we did this in some other time, can have, what was our conclusion? At most, m+1 local extrema. Okay? And so how can we relate, given that constraint, on first sight, it seems that G of omega can have only m+1. M and R are more or less the same, right? R in alternation theory is more or less the same as M. So if we already showed that G of omega can have at most m+1 alternation, and M and R are the same, and alternation theorem tells you need to have at least R+2 or M+2 alternations that achieves maximum and minimum, it seems to me that there's a bit of a mismatch going on, right? G of omega can have no more than m+1, and alternation theorem needs more than m+2 alternations. Are we missing something? No. How do we get ourselves out of this dilemma? Who said that? Correct. It's the endpoints. The F, remember F is union of I1 and I2, and I1 has this endpoint omega p, and I2 has another endpoint omega s, and we talked about closed versus open, the fact that we're talking about closed intervals here. It turns out that when I plot G of omega, okay, it could do something like this, right? So last time when I talked about G of omega having to have at most m+1 local extrema, what are the local extrema? Well, this is one, 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 and then this is one, right? But omega s and omega p, let's say this is omega p and this is omega s. I draw them in a bad way. They're so close to each other. It doesn't matter. But when you look at G of omega, omega p and omega s, they're not local extrema of this at all, are they? No, they don't look like a local extrema. However, in the calculation of alternations for p of x in alternation theorem, you're talking about alternations in those unions of those two intervals, I1, union of I1 and I2. And this is I1, it goes from 0 to omega p, and this is I2, it goes from omega s to pi. So we're talking about alternations here. So it's possible that in the alternation theorem, it's possible that omega p and omega s could be alternation frequencies, even though they're not local extrema here. So because we have, so what I'm trying to say is that because alternation theorem cares about F, which is union of I1 and I2, it's possible, I'm not saying it does happen, but it's possible to have alternations within alternation theorem at omega p and an omega s. Possible to have alternations at omega p and at omega s. Even though omega p and omega s might not be the local extrema of G of omega. Even though omega p comma omega s are not local extrema for G. Okay? So this is the picture of alternation theorem. Again, what we're worried about here is F, which is union of I1 and I2, which is, this is 0 to omega p is I1, and omega s to pi is I2. So it's possible to have alternations right here and right here. And the fact that problem C and alternation theorem always dealt with F being union of closed intervals is good, because if it was open intervals, then we couldn't have alternation at omega s and omega p. So the closed interval thing was a key thing. It's got to be, and thank God we have it. It saves us, okay? Okay, so now that we figured that the end intervals of these I1 and I2 could also be alternations, so coming back here, if G of omega can at most has m plus 1 local extrema, but now it's possible to have omega p and omega s also be a local extrema in these regions. What can we say about the maximum number of local extrema of G of omega in this region, in I1 and I2? So what can we say about total number or maximum number of local extrema of G, not in 0 to pi, but in F, which is union of I1 and I2. It used to be m plus 1 from here to here, from 0 to pi. But now omega p and omega s could also exhibit extrema if we are only concerned about the G of omega in this region plus the union of that region. How many can we have? Total, maximum. It used to be m plus 1 from here to here, but now we're not considering from 0 to pi. We're considering the union of these two and union of these two. Now omega p and omega s can also be local extrema if I'm just considering the union of I1 and I2. So m plus 1 plus 2 is m plus 3. Okay? So that means at most we can have m plus 3 local extrema for G, but in the interval I1 plus I2. Even though in the interval between 0 and pi, omega p and omega s are not local extrema, if I talk about these two intervals, I can have. Why is it m plus 3? Because it was m plus 1 before, and then I add 2 more because of omega s and omega pi. So I get m plus 3. So now let's combine this result with alternation theorem, right? So this is telling me that G of omega can have at most m plus 3 local extrema, and alternation theorem requires at least m plus 2 alternations. So putting those two things together, what can we conclude? If you can have at most m plus 3 and at least m plus 2, what are the two possibilities? Either m plus 2 or m plus 3. Okay, so putting all these things. So alternation theorem tells you at least r plus 2, which is the same as m plus 2. And then this whole argument that we just went through tells you that we have at most m plus 3 extremas. Putting them together, we can say that we either have m plus 2 or m plus 3 local extrema in F. Actually, yeah. Is this discussion clear? Yeah. Coming back to your two questions here, I'm pretty sure I responded to your questions the wrong way. You cannot, this situation here that I talked about, I said this cannot be. It cannot be that you just don't count this x type, what is it, 1, 2, 3, etc. You can't not count, because this achieved a negative, the solution, what alternation theorem tells you is that you cannot have this situation, even if you decide not to count this, because it negates the necessary condition of the theorem. It says if it achieves the minima, if it achieves extrema, it has got to alternate. And because it doesn't, so this situation, my answer to you was, oh, as long as it does, r plus 4, etc. I think that's not true. As long as it achieves extrema, it has got to it has got to be alternating. Okay. So I wanted to make that correct. It falls off right as this part of the theorem, which says it's necessary and sufficient. So in other words, you can't have the extremo and not sort of count it as the alternation. Okay. So you either have m plus 2 or m plus 3 alternations. This is a good point to now take a look at this diagram in Oppenheim and Schaefer. Figure 735. 735. So 30, 34, 35. Okay. If you can zoom in. Okay. Okay. So let's start with this picture. Okay. So that's an example of a low-pass filter that was obtained. That's optimal. It has the minimum. It minimizes the ripple. Optimal in one sense, in a sense that it minimizes the delta 2 ripple or the maximum value of omega in f of absolute value of v of omega 2. It's an optimal, and let's see. Does it? From looking at it, can we say that it satisfies the conditions of optimality? And the first thing you should ask is, what's the order for it? The order for it, he says it's L, and I think the Oppenheim uses L. Okay, it's the same way as we use R. Okay, so which is the same as M. So M in our situations, in our symbology, is 7. Okay? So if M is 7, that means you have a polynomial of order 7. That means you have a 7-tap filter, right? And based on alternation theorem, the unique optimal solution to this should have either 7 plus 2 or 7 plus 3 alternations. So either 9 alternations or 10 alternations, correct? And let's see how many alternations we're getting. First of all, omega equals 0. Is that an alternation? No, because the curve doesn't achieve maxima. Maxima is, it should hit this top line 1 plus delta 1, or the bottom line 1 minus delta 1. So omega equals 0 is not a maxima. It's not an alternation frequency. Omega 1 here, when it hits the bottom here, is 1, right? Omega 2, when it hits on top here, that's 2. How about omega 3, which happens to be omega p? Is that a local extrema? Sure, because when you look at this interval between 0 and omega p, or 0 and omega 3, it does hit that bottom line just before it starts falling down. So that is an extrema. So 1, 2, 3 so far. How about omega s? Is that an extrema? It sure is, because this is the line that shows delta 2, and this is the line corresponding to minus delta 2, and it passes through that corner. So that's the fourth alternation frequency. This was the 5th one, this is the 6th one, this is the 7th one, this is the 8th one, and this is omega equals pi. Does that achieve a local minima? Yeah, it sure does, because it hits minus delta 2. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So if somebody came to you and said, I designed an optimal filter of order 7, and this is the frequency response, can you possibly believe this guy? Is this guy consistent? Yeah. What if he said, I designed a filter of order 5, and this is the frequency response? Optimal filter of order 5. Can you believe this guy? No. With 5, if his order was 5, you would have only had 7 or 8 extrema. This has 9. So it ain't going to do it. What if the guy said, I designed a filter of order 6 that's optimal? And here's the frequency response. Would you believe him? Well, if the filter is of order 6, that means you have to have either 8 or 9 extrema, or 8 or 9 alternations. And would that work here? Yeah, because this guy has 9 alternations. So this could correspond to either an or filter of length, filter of degree. Here is, you have to be careful about what we call it. When your polynomial has m, it goes from 0 to m coefficients. It has m plus 1 taps, right? So if m was 6, this would work. That means if you had a 7-tap filter. If m was 7, this would work. But other than that, it just wouldn't, right? Is this confusing here? Remember, all polynomials, the expression for g of omega is summation n equals 0 to m. So it has m plus 1 coefficients. Yeah? Everybody remembers that? Yeah.
If you have m plus 3 alternations, don't 2 of them have to occur at 0 and 1?
Because then it's, yeah, probably.
This one can't be an L equals 6 because there's no alternation at 0.
Why is it? We'll get to the 0 and pi condition in the next lecture, but let's go over this statement that you just made. Why is it that if you have m plus 3, one of them has to be at 0 or pi? No, the reason it became m plus 3, remember, is because of omega p and omega s. The two that we added, g of omega by itself can have at most m plus 1 extrema, right? The reason we went from m plus 1 to m plus 3 extrema was because we're no longer interested in this whole gigantic interval from 0 to pi, but we're interested in this union of this plus that. And so it was omega p and omega s that did it. But I would defer your question to next time's lecture. We'll talk about the 0 and pi conditions and how these things interfere in next time's lecture. And there's some things to be said about that case. Okay. So let me show you one other picture. Okay. So here Oppenheim is saying we're dealing with a situation where m, in our terminology, is 7, right? So if m is equal to 7, you guys, we're off by quite a bit. Can you zoom out? When m is equal to 7, g of omega has 8 values of a, right? But the number of taps is 2m plus 1. So it's 2 times 7, 14 plus 1. We're all off. The number of taps wasn't m plus 1. You've got to go back to 2 lectures back. It's 2m plus 1, right? So we get stuck with these notations and we have to stick to them. The m here is the same as the m we've been using in our lectures. It's the same as r in alternation theorem. And it's the same as L in Oppenheim's book. So when he says L is 7, that means Rm is 7. That means the number of taps in our filter is 15. It's just a translation between these variables, etc. So here, Oppenheim says, in this example, L is 7. So in our case, M is 7, which means we've designed the filter with 15 tap coefficients. Okay? And question is that a plausible frequency response for an optimal filter of length 15, which is the same as m equals 7? Well, if it is length 7, m is equal to 7, it could have 9 or 10 alternations. So what does it have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So good. That's a kosher thing. That could be possibly an optimal filter. Come down here now. And again, m is equal to 7. So we could have either 9 alternations or 10. How many have we got? Is this an alternation? No, it doesn't hit that. It doesn't hit that line up here. So 1, 2, 3, 4. It passes through omega as 4. 5, 6, 7, 8, 9. Can that be a possible filter for m equals 7? Yeah, it's got 9 alternations. Let's go down one more. So in this case, 0 and pi were both part of the thing. In this case, 0 was not an alternation, but pi was. Let's go down one more. And what we have here is, how many alternations do we have? 1, 2. Can you sharpen the image just a little bit, the focus? Thank you. Okay, so we have 1, 2, 3, 4. Again, it passes through here. 5, 6, 7, 8, 9. And does it is pi a possibility? No, it doesn't achieve all of them. So 9. So it's still good. And then the last one, let's count it. 1, 2, 3, 4, 5, 6, 7, 8, 9. So here you have alternation both at 0 and at pi. Okay. So in the last, if you zoom out now, we can show the whole page. So in the last 3 filters, we had 9 alternation, and in this one we had 10. So this case where we have 10 alternation is called the extra ripple case. Just the name for it. Okay. Yeah. So that's that. So these are examples of how this alternation stuff work. Okay. So do we have more time for me to talk about the algorithms? I think I'm going to stop at this point, and I'll go over the various sort of properties of these things on the next lecture. I also want to talk about one more important thing, and I'll get your question in just a second, and that's why I don't want to end this whole discussion in today's lecture, and that is, so far, alternation theorem is a bunch of mumbo-jumbo. It says, there exists a unique polynomial. Good, I'm so happy it's unique, but where is it? How do I compute it? I never told you any of that, so which is what we're going to talk about next Friday's lecture. And then I'll also talk about some of the properties that one can confidently say about these maximums and minimums and stuff like that. Question?
Yeah, since alternation theory says there's a unique solution, so I guess only one of those 4 could be.
Exactly. When I plotted these, I didn't mean to say that there was 4 polynomials having these 4. Oh, I'm so glad you mentioned it. I didn't mean to say there's 4 polynomials or 4 filters doing these. That was not my intent. I'm saying the optimal, the unique thing that we don't even know where it is, but we can find it using the algorithm I'll tell you next time, behaves in one of these 4 ways. But it doesn't mean there's 4 filters doing 4 different things. There's only one of them. Right? There's only one m equals 7, that means 15 tap filter, that does one of these 4 things. Period. No more. That minimizes the delta 2. That given those specs, there's only one that does it. Thank you. Yeah, one more question.
We talked about in the alternation theory that you had this norm of E.
Mm-hmm.
You look back in the picture in 734, the first figure that you showed.
Mm-hmm.
Yeah, this one.
Mm-hmm.
It looks like we have different heights for the alternations in the different bands, so it's like kind of a different delta E, or norm of E.
Oh, no, but delta E. Ah, that was a good question. You got tricked. The E thing had the K. Remember? Let me show this. This is going to give you your answer, either page 5 or page 6. The E thing is the same, right? But the G thing, it's plus theta minus theta, plus delta 2 minus delta 2. But the G thing is theta K in this range and theta in the other one. And why is that? Because this delta 1 is different from delta 2. And that K factor made both of them be the same, right? In the E, they're the same, but by the time you get to G, there's delta 1. And that was one of our motivations for doing optimum filter design, because when delta 1 and delta 2 were different, when the passband and stopband requirements, ripple requirements were different, the window design didn't care. It just, you had to pick the smaller of the two and proceed and solve the problem. Here, God, you hit it. It's delta 1, smack delta 1 here, and smack delta 2. And there's only one filter that does it, no more than one. So case closed. That's why this was such a good idea in 1975. No more research needed. Finished. Yeah.
Since the alternation theorem says there need to be at least R plus 2
Mhm.
alternation, and the filter constraint that says there could be at most R plus 3, is it possible that we don't get a solution at all?
It's a good point. Because they both talk with at most and at least, but the thing is that alternation theorem talks about that. If you come back here, let's look at the statement here. It says it's a necessary and sufficient condition for a unique thing is to minimize this, is to have that. So as long as, in other words, what you're talking about is existence. Does the alternation theorem guarantee existence? Is that what you're saying?
Well, the alternation theorem guarantees the solution to this problem, but
No, it doesn't guarantee existence. It characterizes the solution if it exists in some way. And my answer to you is, yeah, it's possible. For example, I could be extremely unreasonable. Okay, I could come to you and say, design me a filter of a filter, FR filter with, I don't know, 9 coefficients that has ripple of 0.001 in passband and 0.012 at stopband. And for God's sake, you can't design something. So that doesn't guarantee existence. It says if it exists, it has got to do these and only these. And if it doesn't do these things, it won't exist. Okay? One other question. So yeah, you could be, that sharp cutoff that everybody wants, the box-like. I can come up with such tough specs that the thing won't happen. It won't happen at least at that R. I mean, you could jack up R to make it happen. But if I came to you and said, give me a 3-tap filter that does this, you can just shoot me and get rid of me because it doesn't exist. You can't be unreasonable. One more question. Okay. So good luck in the midterm. I won't be there on Wednesday, but I will have email access between now and Wednesday if you have any questions. And I'll see you next Friday.